Hello friends and welcome to a lecture on numerical computation methods. Today we will use Python programming, or we will write a Python program to find the roots of a multivariable equation using Newton-Raphson method. Now let's remember one thing. If you have an equation with two variables, you need two equations to find the roots. And if you have three variables, then you need three equations to use Newton-Raphson method to find the root. So as many the number of variables, that many is the equations that you should be having. Now in this case, we have a two variable problem, that is x and y are the variables. And the equations given to us are x square minus y is equal to 1 and x minus y square is equal to minus 1. Now as usual, the method for finding the root is xn plus 1 is equal to xn minus fx upon f dash x. Well, what is this exactly? Xn is the old estimate of the root. That is, xn now in this case would be a array which would have the values of x and y at any point. And then afterwards, fx will be also an array of the functions, and f dash x would be the Jacobian of it. Well, how it's done will be very clear in a little while. So first we go ahead with importing all our libraries. So we import Sympy. Then we import from sympy.abc import x, y, z, a, b, c. So this imports all the simples. Then from Sympy import star. So this imports all the libraries in Sympy. And then finally we import numpy. So we import numpy as np. So all the libraries are imported. Now the function f is written as a matrix, and therefore we write m is equal to matrix matrix, and the first row of the matrix is the first function, so it's going to be x square minus y minus 1, and the second row of this matrix is the second function. So we again put square brackets and we write x minus y square plus 1. So let's see the output of f, and there we have this matrix. Now the f dash x is nothing but the Jacobian of this function f. Now how do we calculate it? So we find f Jacob, Jacob. So that is just a variable which will store the Jacobian. So we write f dot Jacobin, Jacobian, and in square brackets the Jacobian with respect to the variables. Now let's see the output of f Jacob. And there, as you can see, we have got the Jacobian. Okay. Okay. Now, fx over f dash x, this can be seen as the improvement in the value of the values of x and y. Okay. So, how do we now write it as improvement is equal to f So what we have essentially done is taken this Jacobian matrix in the numerator. So we have taken the inverse of this matrix and multiplied it by the function matrix. Okay. Now to find its value at any point, we write it as SUBS subs, that is short for substitute. That is for X and that is the bracket for Y. Then we write X comma 2 and we write Y comma 2. And let's see what is the value of improvement that we have. There, as you can see, we get it as 1 by 3 and 1 by 3. Now, mind you, this is a matrix and it is a column matrix. Now, the initial values of X and Y can also be taken up as a column matrix. So, what do we do here? We write A old, which is the matrix for initial values, or the column matrix for initial values of X and Y. Write it as matrix and start the matrix. Now, the first row of the column matrix is going to be 2. And the second row of the column matrix is also going to be 2. Then we write here A old 0, which will read the value of X. And we write here A old 1, which will take the value of Y. And let's execute this now. And as we can see here, we have again got 1 by 3, 1 by 3 now. Now, having understood how the improvement is going to be calculated, now we calculate A new, that is the new estimate. The new estimate is going to be nothing but the A old minus the improvement. So we see what is A new. And as we can see here, we get the updated matrix. The A new, we get it out, right? Okay. Now let's see what happens if we put the value of A new and again execute this. So we put 5 by 3 here and 5 by 3 here. And again execute this. Now we have got 1.619, 1.619. So let us put this value now. 1.619 and 1.619. And let's execute this once again. And as we can see here, there is very little improvement here. So we have pretty much converged to the root. Now, this can be done using a for loop. So for that, all we have to do is take this and move it. So now we take the old value of A old, that is 2, and we write the follow for iteration in range. Let's do the iteration for 3 times. There we have now. Now the A old will be equal to the A new for the next iteration. And finally, let's print out A new after 3 iterations. And let us see what do we get. So we have got 1597 over 987, 1597 over 987, and let us do it for 4 iterations now. And let us do it for 5 iterations now. And let us do it for 6 iterations now. Okay. Now let us see what we exactly get here. So for that, what we can do is we can write here 0 and we can write here a new 1 and we can write this as float. So this will give us the values in decimals and we write it as FLOAT, float. So let's run this now. And as we can see here, pretty much we have converged to the root by doing the iterations. Now we can write a while loop also in this. Okay, now how do we solve this using while loop? So let's look at it. So let's copy down the code first to implement the while loop. There we are. And the essential code, of course, in the next line. This is the essential code for calculation. There we are. And there we are. Now we define something known as diff rms is equal to 1. Now I'll later on explain you the meaning of this variable, but let's do something now. Let's define something known as diff is equal to a new minus a old. Okay, and print diff. Right, and that's it. So what we have here is, let's take this code here and cut it and paste it below this. So because the a new is getting estimated here, right, there we are, done. And let's run this. So as you can see here, this gives you the value between the difference or the difference between the old and the new estimates, right? Now what we do here is we convert this into an array. So we put np.array array. So this is what we get. Now the beauty with this is that when you convert it into an array, what you can do is you can also square the individual members of this, right? So the other thing that we can do is we can sum up the individual members also. So there we get the sum. And then afterwards, we can take the root of that sum. So there we have this square root of the sum. So this is nothing but the diff RMS, that is the root mean square difference. And let's see, that is what we get. So now what we can do here is take all this code and start writing our while loop. So while diff RMS is greater than 0.001, and then we shift the code so that it is in the while loop. So now what is going to happen here is it is going to do the improvement. It is going to calculate the new value, then take the root mean square difference and substitute the old with the new. And this while loop will keep continuing. Now let's do something here to check the iterations. We define a variable iteration. And for each iteration, it is going to print out, it is going to calculate the number of iterations that it has done. So we come here and we write itrn is equal to itrn plus 1. Now this is the iteration counter. And then finally we print the iterations. And we also print the roots. A new 0 and a new 1, and we write float, we put it in float so that we get the decimal values. And let's see. Okay, there we are. We are done. Now, as you can see, after 4 iteration, it converges. And this does the required number of iterations which is required to converge to the roots. So let us take another root here, 0.001, and let us take this as minus 0.9. And as we can see here, we get 0 and minus 1. So this is also one of the roots, 0 and minus 1. The other root is, of course, let us take now minus 0.9, and the other root, of course, is minus 1, 0. And now let's take minus 0.4 and minus 0.4. And as we can see here, this is also one of the roots. So required number of iterations are always done. Now, this is a much more elegant way of doing things. But you have to be very careful with implementation of while loops, because supposing the condition is not satisfied, the while loop will keep executing. But for the for loop, at least we have a guarantee that yes, after 100, 200 or 300 iterations, it will finally stop. So you have to be careful with the while loop. So the better part is you first write what is going to be in the while loop, check it once, and then write the while loop so that you're very sure that the while loop will terminate. So that was all about how do we write a Python code for Newton-Raphson method for multivariable equations. Now this can be written for 2 variables, 3 variables, 4 variables, and so on. Okay guys, have a great day. Bye.